Okay, let's look at some problems for conservation of energy. Number one, we're given first a ball with a mass of 125 kilograms is held a height of 25 meters above the earth. And then it wants us to find the potential energy of the ball. And so our solution, then, we're going to use our formula that potential energy equals mass times gravity times height. So it's going to equal then what? 125 kilograms times our gravity. We use metric here for 9.81 meters per second squared times our height of 25 meters. When we multiply that out, we're going to get then 30,656 kilogram meters per second squared times a meter. I write that because a kilogram meter per second squared is a Newton, right? So that would be 30,656 Newton meters. And then we box our answer. Okay, number two, we're given a ball with a weight of 55,000 pounds is held at a height of 50 miles. What is the ball's potential energy in kip feet, where one kip equals 1,000 pounds? And we are to find the potential energy. So our solution then is potential energy equals mass times gravity times height. But remember, the mass times gravity is weight. So we have the potential energy then is equal to the 55,000 pounds. That's mass times gravity, 55,000 pounds. But we don't want pounds, we want it in kips. So we got to use our conversion. One kip is 1,000 pounds. And then we can cancel out the pounds. Now we have kips, 55,000 divided by 1,000 kips, times the height, which is 50 miles. But we need it in feet. So we got to convert that to 5,280 feet divided by 1 mile, right? That's how many feet in a mile. That allows us to cancel out the miles. Okay, so now we've got kip feet, and when we multiply that out, we'll get a very big number, 1,452,000 kip feet. And then we box it. Okay, let's look at problem 3. In problem 3, we're given a mass of 2,500 grams is dropped from 15 meters, so a height of 15 meters on Earth. What is the weight's velocity right before impact? So we want to find the velocity at impact. Now our solution is, remember, we're going to use our formulas that we derived in the previous video, and in our hints, the velocity is equal to the square root of 2 times the gravitational constant times the height. So in this case, we've got the square root of 2 times the gravitational constant on Earth, and since we're using meters, we'll use metric, 9.81 meters per second squared times a height of 15 meters. And when we work that out, we find that the velocity then is 294 meters per second. And of course, we need to box that answer. Now, number 4 says if you have a 200 kilogram ball on the moon, okay, so we're given a mass of 200 kilograms on the moon. It's raised to 25 meters, so we have a height of 25 meters. And it says, what is the potential energy on the moon? And we're going to need then the gravitational constant, which is the gravitational constant on the moon is 1.622 meters per second squared. Okay, and we want to find the potential energy on the moon. Okay, our solution then is our potential energy equals the mass times the gravity times the height. So the mass is 200 kilograms. The height is 25 meters. And the gravitational constant of the moon is 1.622 meters per second squared. Okay, so we multiply that out, we see that the potential energy on the moon of this 200 kilogram ball is 8,110 kilogram meters per second squared times a meter. And remember, that's because this is a Newton, so we have 8,110 Newton meters. And of course, I need to box my answer. Okay, number 5. A ball weighs 55 pounds on Earth, is dropped 200 feet on Mars. What is the potential energy just before you drop the ball? Now, for this one, we're going to need to use gravity on Earth and on Mars, right? Now, the reason we have to use it, so let's look at what we get. First, let's see what we're given. We're given that the weight on Earth is 55 pounds. And the height that we're going to drop it from is 200 feet. And we're also given that the gravity constant, GC on, I'll put M on Mars, is 12.1760 feet per second squared. Okay, so we want to find the potential energy on Mars. And our solution then, okay, now our solution is, the first thing we've got to do, we have to get the mass of this ball. Now the mass, remember that the weight equals mass times gravity. So the mass of this particular ball is going to equal its weight divided by the gravity. So the weight here on Earth is 55 pounds divided by the gravitational constant of Earth, which is 32.2 feet per second squared. Now I'm going to leave the mass like that. And then we'll do the potential energy, and we'll do the potential energy. The potential energy is mass times gravity times height, right? So we're going to use our mass. Well, our mass is the 55 pounds divided by 32.2 feet per second squared times our gravity, which is, now we're going to use the gravity on Mars, because that's where we're interested in the potential energy, is 12.176 feet per second squared. Now notice the gravity on Mars is much smaller than Earth. So what does that tell you? That tells you the gravity, that the mass of Mars is smaller than Earth, times the height of 200 feet. Okay, now what we've got here, you'll notice that these units here cancel out. So all we're left with is foot-pounds, and that's what we want. Potential energy in the English system will be in foot-pounds. So that's good. So now let's calculate it. The potential energy then is going to equal then 55 divided by 32.2 times 12.176 times 200. And when you calculate that out, you should get 4,160 foot-pounds, which I will box. Okay, on number 6, if you drop a ball that weighs 50 pounds on Earth from 1,500 feet on Jupiter, what is the ball's velocity right before impact? Okay, here we're given a ball that weighs 50 pounds. Now, it weighs 50 pounds. So remember, that's mass times gravity. And the height is 1,500 feet. Now, it says, what is the ball's velocity? So what we're trying to find is the ball's velocity, v, at impact, not on Earth, but on Jupiter. Now our solution here, really, it doesn't really matter if it's the mass, does it? Because we know that we're going to use the velocity equals the square root of 2 times the gravity times height. In this case, we know that we've got the velocity is going to equal the square root of 2 times gravity. Now the gravity will be that on Jupiter, which is 81.332 feet per second squared, times then the height, which is 1,500 feet. And when we do that calculation, we see that the velocity is 494 feet per second at impact on Jupiter. So now go to your workbook and do the problems for conservation of energy there.